For years, scientists have convinced us that the universe is constantly expanding. This belief has fascinated scientists and academics, who have adopted the Big Bang theory as the most widely accepted explanation for the origin and evolution of the universe. According to this theory, the universe began in an extremely dense and hot state and has since undergone continuous expansion. However, the James Webb Space Telescope has made a surprising discovery that challenges this theory. How did the Space Telescope challenge the idea of expansion? And what does this mean for our understanding of space? Join us as we take a look at the recent shocking find from the legendary James Webb Telescope. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel. Be sure to like this video and turn on the notification bell. Albert Einstein's general theory of relativity provides a framework for understanding how the press of heavy objects bends spacetime. According to this theory, the cosmos originated as a singularity, a point of infinite density and temperature, approximately 13.8 billion years ago. According to the Big Bang theory, all matter and energy were compressed into an extremely small, hot region at this point. The cosmos began to expand with a rapid and violent event known as the Big Bang. During the first few seconds following the Big Bang, the singularity experienced a massive release of energy. The universe was filled with an extremely hot, dense, and energetic plasma containing protons, neutrons, electrons, and their antiparticles. As the universe cooled due to its expansion, the temperature dropped enough to allow electrons to bond with protons and form neutral atoms. This process, known as recombination, allowed protons to move freely through space, resulting in the cosmic microwave background radiation that we can detect today. The stretching of space and time itself may represent the expansion of the universe. This stretching does not imply movement through space where objects move away from a central point, but an expansion of space itself. We can imagine it as the surface of an inflating balloon. The points on the surface move away from each other as the balloon grows, not because the points are moving, but because the space between them is expanding. Similarly, in the case of the universe, galaxies and other celestial objects are pulled by the expansion of space rather than away from it. So, what is the source of this expansion of spacetime? According to scientists, dark energy is a hypothetical form of energy thought to permeate all space and exert a negative pressure. This dark energy is thought to be the cause of the accelerating expansion of the universe. In recent decades, observations have revealed a phenomenon crucial to understanding the importance of dark energy, the balance between gravitational forces and the expansion of the universe. Gravity, an attractive force acting on massive objects, tries to slow down the growth of the universe. If the universe were composed solely of matter, such as galaxies and their corresponding mass, gravity would eventually stop the expansion and give rise to a phenomenon known as the Big Crunch. However, observations reveal that the expansion of the cosmos is accelerating rather than slowing down. This implies the existence of a repulsive force that counteracts the effect of gravity. This repulsive force is generated by dark energy, which is uniformly distributed in space and exerts a negative pressure. The precise nature of this energy remains one of the greatest mysteries in modern cosmology, and scientists are actively investigating its characteristics. Although dark energy is responsible for the accelerating expansion, the distribution of matter in the universe also plays a crucial role. The density of matter and energy influences the curvature of spacetime through the equations of general relativity. Regions with higher density exert a stronger gravitational pull, which slows down the expansion of the cosmos. On the other hand, regions with lower density experience weaker gravitational attraction and contribute to the overall expansion of the universe. Matter in the universe is not uniformly distributed but is organized into massive cosmic formations, such as galaxies, clusters, and superclusters, which are interconnected by vast cosmic web-shaped filaments. These structures form due to the gravitational collapse of regions with higher density under the influence of gravity. As the universe expands, these cosmic formations experience a stretching of spacetime. However, gravitational forces within these structures counteract the expansion to some extent, resulting in a complex interaction between the expansion of spacetime and the gravitational pull of mass. On larger scales, the expansion takes precedence, resulting in a continuous stretching of the cosmic web. It is important to note that the expansion of the universe does not imply that galaxies are moving away in space. In fact, galaxies may move closer together on smaller scales due to the influence of gravity. However, on a larger scale, the overall effect of the expansion is to increase the distances between galaxies over time. Various observations and abundant evidence support the expansion of the universe. One important example is the redshift of light emitted by distant galaxies. As the universe expands, the wavelengths of light from these galaxies are stretched, shifting towards the red end of the electromagnetic spectrum. This phenomenon, known as the cosmological redshift, provides compelling evidence for the expansion of spacetime. Another crucial piece of evidence is the cosmic microwave background radiation, CMB, which is a remnant of the hot early universe. The CMB shows a surprisingly uniform distribution of energy across the sky, with small oscillations that reveal important information about the initial conditions and subsequent evolution of the universe. Extensive CMB investigations have confirmed predictions of an expanding universe and strengthened the Big Bang theory. Observation of data from large-scale surveys, such as the Sloan Digital Sky Survey and the European Space Agency's Planck satellite project, have provided accurate information in recent years about the expansion rates of the universe and the distribution of matter and energy within it. These discoveries have improved our understanding and contributed to ongoing research for information about the underlying nature of the universe. One of the most fascinating aspects of the James Webb Space Telescope's galaxy survey is its ability to map the large-scale structure of the cosmos at high redshifts, when galaxies were still young and grouped into large clusters known as protoclusters. These protoclusters are the predecessors of today's galaxy clusters, which are the largest gravitational structures in the universe. By studying these protoclusters, we can learn about the interactions between galaxies, their interactions with their surroundings, their growth and merger, and how they influence the formation of stars and planets. Protoclusters are extremely rare and difficult to find because of their wide expanse in the sky and low surface luminosity. However, the James Webb Space Telescope's wide-field, high-sensitivity cameras will make it possible to detect hundreds of miles of galaxies in a single observation, covering a significant portion of the sky with unprecedented depth and detail that has never been observed before. Astronomers have the ability to identify protoclusters by analyzing galaxy density, spectral properties, and spatial dispersions. To do this, they combine data from the James Webb Space Telescope with other observatory surveys. The James Webb also provides information on the masses, ages, star formation rate, dust content, and gas kinematics of individual galaxies within protoclusters. These observations will reveal the differences between galaxies within protoclusters and those in less dense environments, as well as their evolution over time within their hot structures. In addition, the JW will allow investigating the intergalactic medium, IGM, around protoclusters, which is enriched by supernovae and active galactic nuclei, AGN. The IGM regulates galaxy formation by supplying gas for star formation and withdrawing it through winds and outflows.